Welcome to the deep dive. Today we're jumping into something really interesting, a turbine technology developed by Brian B. Williams. It sounds quite innovative.
It really does. We've got a stack of materials here, white papers, analyses, comparisons, all focus on this unique design.
Yeah, we'll be looking at performance data for a couple of different sizes, a 13-inch and a smaller 3-inch model, and comparisons to, the usual ways we generate power.
There's also a crucial piece clarifying some of the efficiency numbers, which we definitely need to unpack, and how it links up with a special kind of generator.
Our mission really is to get our heads around this bladeless concept. What makes it tick? What are the supposed benefits? And what could it actually mean for you, the listener?
And the core idea, the big shift, is moving away from traditional blades. Instead, it uses vortex formation, basically, controlled swirling fluid to capture energy.
Right, and that fundamental difference is apparently the key to a whole host of claimed advantages.
Exactly. It sets off this cascade effect we'll explore.
Okay, let's start with the bigger one, the 13.3-inch turbine. The white paper goes into quite a bit of detail on the internal flow analysis.
And importantly, it's not just simulation. They apparently built and tested a physical unit too.
Designed initially for R245 half a refrigerant, but it seems flexible, adaptable to other fluids.
Which is a point we'll probably come back to. But the headline number that jumps out is that efficiency claim around 42.5% thermal to mechanical.
And that figure holds for both the simulations and the physical tests, according to the paper.
Yeah, and they really dug into the flow dynamics, pressure drop, temperature changes, density, velocity, even the Mach number along the turbine's length.
So things like the pressure dropping steadily, about 8.8 psi, that shows energy extraction, right?
Precisely. It indicates work is being done. The temperature profile is interesting too, over a 500-degree Fahrenheit span mentioned.
And the data suggests a smooth laminar flow, which is good for efficiency, and that the vortex is engaging properly with this scalloped rotor design.
Getting that optimal energy transfer. The velocity approaches supersonic speeds in parts, and the Mach number gets close to transonic, showing some serious fluid dynamics at play.
The paper also puts it up against gas turbines, steam expanders, Stirling engines.
And claims it comes out favorably in power density, potential lifespan they estimate over 25 years, and that efficiency figure.
Plus, that list of potential working fluids is quite long. Other refrigerants, toluene, even steam. Seems very versatile.
That adaptability is a potential game changer. It suggests they could work with various heat sources, different temperature ranges.
And that 25-year lifespan claim, if that holds up with minimal maintenance, the cost savings could be huge compared to systems needing constant overhauls.
Definitely a significant point. Now, what about the smaller 3-inch version? It's referred to as a gas turbine in one analysis.
Right, I noticed that too. But other documents clarify it's the same bladeless vortex principle. This analysis is a CFD simulation, computer modeling.
Computational fluid dynamics, yeah. Basically a virtual wind tunnel.
Yeah.
Allows them to see things that are hard to measure physically.
And this sim, run in April 2025, gives us a lot of numbers. Enthalpy in and out, temperatures, pressure drop, about 8.7 bar this time, horsepower.
And a simulated efficiency of roughly 65%. That's quite a bit higher than the 13-inch model's 42.5% we just discussed, at least in this specific simulation.
It is. The report notes high energy output, stable mass flow, which sounds good.
But it also flags a slight decrease in efficiency compared to maybe earlier runs and more pressure variation.
Why would that be?
Well, they mentioned using a reduced cell count for the simulation, over 3.6 million cells, and fewer iterations, 348, probably to speed up the calculation.
So maybe a trade-off, faster results, but maybe slightly less precise?
Could be. It's common in CFD. But still, getting a 65% efficiency number, even with those caveats, is definitely attention-grabbing.
Absolutely. Okay, let's shift to the inventor's perspective. There's a document outlining the advantages claimed by Brian Williams himself.
Right, he emphasizes flexibility. On-demand startup in seconds, apparently.
High efficiency, attributed to this jet ring and rotor design. And a really interesting point, it can act as a flywheel.
Yeah, that's quite clever. The spinning rotor has mass, stores kinetic energy. That helps stabilize power output, smooth things out.
He also mentions it being compact, scalable, needing lower fluid temps than typical steam turbines.
Which again points to broader applications, and the manufacturing aspect using standard CNC machines, common materials like aluminum, suggests lower production costs could be possible.
It definitely paints a picture of an accessible, versatile technology. He seems focused on meeting future energy needs, not just current ones.
A big vision. Now, that CFD simulation summary document gives us a head-to-head comparison.
Right. This puts the 3-inch bladeless turbine 2.0 directly against Stirling engines and conventional bladed turbines of similar size.
And the claim differences are stark, especially on cost and lifespan.
The numbers are kind of staggering. Bladeless cost, $1,200. Stirling, $10,000. Bladed, $12,000. That's a huge difference.
And lifespan. 25 plus years with no maintenance for the bladeless versus maybe 10, 15 years with moderate to high maintenance for the others.
Then there's the energy cost per kilowatt hour. It claims 0.0048 cents for bladeless, compared to nearly 7 cents for Stirling and 12 cents for bladed.
If those numbers hold up in the real world, wow, plus the environmental claims.
Near zero CO2 emissions, minimal waste, almost silent operation for the bladeless design, and very high scalability.
It really stacks up favorably in this comparison. The summary also mentions CFD results for the 13.3-inch using CO2, showing stable flow, consistent torque around 22 pound-a-foot wind, and reiterating that 42.5% thermal to mechanical efficiency.
And it notes those symmetric vortices helping the energy exchange. Seems like managing that vortex is absolutely critical.
It's the heart of the design. If these comparisons are even close to accurate, it could genuinely disrupt several sectors.
Okay, but let's address the elephant in the room, those efficiency numbers, especially the 65%. The Carnot confusion paper tackles this directly.
Yes, this is a really important clarification. The inventor states that the efficiency figures, like that 65% for the 3-inch sim, refer to mechanical conversion, how well it extracts energy already present as fluid motion or pressure.
Not thermal to work efficiency like a traditional heat engine converting heat into rotation.
Exactly. And that's crucial because Carnot's theorem, the theoretical limit for heat engine efficiency, doesn't directly apply in the same way here.
He uses the analogy of a Pelton wheel water turbine, right, which can be like 90% efficient mechanically.
Right. It's converting the potential and kinetic energy of the water into rotation. He argues the high temperatures seen in his turbine are incidental, maybe from friction or fluid dynamics, not the primary energy source being converted in the way a heat engine uses heat.
So the high efficiency isn't violating fundamental laws because it's measuring a different kind of energy conversion. He even claims a 30% performance gain over conventional turbines in similar mechanical efficiency tasks.
It's a critical distinction for understanding where these numbers come from and why they might seem so high compared to typical thermal efficiencies. It makes the figures more plausible if you frame it as mechanical energy extraction.
And there's even a piece analyzing a NASA video trying to validate this independently.
Yeah, using input parameters from the video, 100 psig nitrogen gas, 12 SCFM flow into a 10-inch turbine, producing 440 watts output.
The calculation, assuming adiabatic expansion down to atmospheric pressure, yields about 44% efficiency.
Which is pretty close to the inventor's claim of 45% for a similar setup in that context. It adds a bit of external weight to the claims.
Okay, let's look at how this matters. This one contrasts the bladeless design with traditional bladed turbines again, focusing on the mechanics.
Right, blades rotating under stress versus energy transfer via viscous drag within this incredibly fast vortex, 130,000 RPM mentioned here.
Wow, 130,000 RPM for the vortex. And the efficiency comparison again, 35% for small bladed versus over 64% claimed for the bladeless.
And the complexity and lifespan argument returns. Intricate blades prone to failure versus a simple design aiming for 25 plus years maintenance free. Fewer failure points.
This document gives some wild speed figures too. That 130,000 RPM vortex in a 0.25-inch diameter means fluid speeds of 96.6 miles per hour.
But the rotor itself, the part that spins to generate power, is turning slower at 65,000 RPM.
Yet, because it's larger, 2.9 inches diameter, the linear speed at its edge is much faster, 560.4 miles per hour.
So the analogy they use is hurricanes rotating at 96 miles per hour inside of a rotor traveling at 560 miles per hour. That really paints a picture of the forces involved.
It does. Using that high-speed internal vortex to drive a larger, albeit slower spinning, rotor seems key to how it works.
It's a unique approach to energy transfer, potentially reducing stress on the main moving part while capturing that vortex energy.
Now, there's a document about Jethro described as a jet engine application.
A decompression core vortex expander with thermodynamic mixing? Sounds complex.
For a 3-inch Jethro running hot combustion gases 1800 Kelvin down to 900 Kelvin, the estimated power is huge, 1.42 megawatts.
That highlights the potential power density, especially under high temperature conditions. The decompression aspect is interesting, suggesting it works by expanding gas rather than compressing it first like conventional jets.
It mentions those micro hurricane vanes at 130,000 RPM, creating intense mixing and shearing for combustion, while the main rotor at 60,000 RPM controls the expansion and energy extraction.
The document also looks at inlet flow constraints, estimating about 0.044 kilograms mass flow through two small tubes. And it describes the process: vortex activation, rotor suction, combustion, thrust.
Again, the claim is high energy density compared to conventional jet dynamics. Suggests potential beyond just stationary power, maybe aerospace.
It certainly seems possible given the claimed power to size ratio, a very different approach to propulsion.
And the innovation doesn't stop there. The QPE white paper introduces a plasma-enhanced boundary layer turbine.
Plasma enhanced. Okay, now we're getting really advanced.
This is a 6-inch system claiming an even higher total system efficiency, 86.8%.
86.8%?
Oh. It involves synchronized plasma pulse injection, precise jet timing, and enhanced boundary layer control using an optimized scallop design. It operates at 5.2 hertz, producing 56.4 kilowatts.
So using plasma pulses to, further optimize the vortex formation and energy transfer?
Seems like it. Better control, maybe more efficient interaction with the fluid. The paper details the plasma system operating at over 11,000 Kelvin with magnetic containment and an optimized gas mix.
That's definitely pushing the envelope. It shows continuous development and refinement of the core vortex idea, integrating other advanced physics.
Okay, so you have this potentially highly efficient turbine spinning very fast. How do you turn that rotation into electricity? That's where the switched reluctance generator, the SRG, comes in.
Right, and there are documents specifically about an SRG designed for this T2.0 turbine technology, built for extreme environments and high speeds over 13,000 RPM.
A key feature seems to be using those scallops on the rotor, but this time with an optical encoder.
For precise rotor position detection, SRGs need to know exactly where the rotor is to switch the stator electromagnets at the right moment for efficient generation.
And the SRG rotor itself is simpler than in many generators, right? No windings, no permanent magnets.
Exactly, just a shaped piece of ferromagnetic material. That simplicity makes it robust, ideal for high speeds where windings or magnets might fail.
The dedicated SRG white paper goes deeper. It targets 89% efficiency between 7,200 and 16,000 RPM.
That's a very high generator efficiency, crucial for not losing the turbine's gains during conversion to electricity.
It uses special laminated steel cores, a triple tri-core coil setup connected in series, aiming for a max voltage output over 6,500 volts.
High voltage potential. And it mentions active water cooling with optical temperature control, necessary for managing heat at those power levels and speeds.
Details like wire gauge, turns per coil, rotor design, power output range, 15.9 kilowatt up to 61.5 kilowatt are all laid out. The focus seems to be on maximizing magnetic force and flux linkage for efficiency.
It sounds like a generator specifically tailored to complement the high-speed, high-efficiency potential of the turbine. A robust, scalable design aiming for minimal environmental impact itself.
So turbine and generator designed to work together efficiently. Now, zooming out, the future of energy analysis ties this all together.
It positions the technology as a potential solution for decentralized power generation, addressing issues like aging grids and the intermittency of some renewables.
Right. It contrasts it with solar and wind limitations, grid integration challenges, and presents the bladeless turbine, especially using a refrigerant cycle at lower temperatures, as a source of continuous 147 on-demand power.
The decentralized argument is strong. Less reliance on long transmission lines means lower losses, potentially greater grid resilience.
The analysis hammers home the advantages: scalability, adaptability to various heat sources, long life, environmental benefits like reduced emissions and land use, no toxic materials.
And economic benefits too: reduced infrastructure costs, lower maintenance. It suggests it could fit within existing utility models or enable new ones, residential, commercial, utility scale.
It really frames it as a potentially transformative technology for a more sustainable and resilient energy future.
And that presentation document just visually reinforces all those points.
Yeah.
Environment, cost, lifespan, efficiency, scalability. The core message is consistently about a leap forward.
Okay, so wrapping up this deep dive, we've covered a lot of ground on Brian Williams' turbine tech.
Yeah, the absolute core is that bladeless design, using vortex mechanics instead of physical blades. That seems to be the foundation for everything else.
And stemming from that, We see claims of higher mechanical efficiency, much lower manufacturing costs, significantly longer lifespans with little maintenance.
Reduced environmental impact emissions, waste, noise, and high scalability from small units potentially up to larger power generation, maybe even aerospace.
And the integration with that specialized switched reluctance generator, the SRG, aiming for high electrical conversion efficiency too.
Some of the specific claims are really striking, aren't they? That 64% simulated efficiency for the 3-inch, the potential 86.8% for the plasma version.
Absolutely. And the cost and lifespan figures compared to traditional tech. That image of the 130,000 RPM vortex inside the rotor, it sticks with you.
And the adaptability to different fluids and heat sources hints at wide applicability. Plus, that crucial distinction between mechanical and thermal efficiency is key to interpreting the numbers correctly.
So for you, the learner, hopefully this gives you a solid understanding of a potentially disruptive technology, whether you're tracking sustainable energy, power generation advances, or just curious about new inventions.
Understanding the principles and the claimed benefits of this bladeless turbine offers real insight. Its potential for decentralized power, if realized, could significantly change how we think about energy access and grid stability.
Which brings us to a final thought to leave you with.